So when it comes to complex number, there's an interesting fact that we can actually represent them using graph. So this is an example. So let's say we have the complex number 3 plus 4i, and we want to represent them in a graph. That is actually called the Argand diagram. So this is what we call the Argand diagram, and this is the imaginary and this is the real part. Now the real part is 3. So real part you get 3 units, that 3. Imaginary is 4i, so that 4 unit. And this is the point of 3 plus 4i. Now this can also be written as vector as 3 or 4. So 3 unit to the right and 4 unit up. And similarly, we can also represent another, say we have 2 plus I. So we can represent them as 2, 1. So that will be this point. And an interesting fact about this point is that we can actually make calculation on them as vector. So let's say we want an addition. So we want an addition of these two complex numbers. So we got 3 plus 2 is 5 and 4 plus 1 is 5. So that gives us 5, 5. Now if we represent it here, so so here we have 1, 2, 3, 4, 5, 3, 4, so 5 approximately here. Now if we draw it this way, so if we draw a line that is parallel to this line, another line that is parallel to this line, starting from these 2 points, we actually made a parallelogram. So this is a parallelogram. And funny thing about the diagonal of this parallelogram is this diagonal is actually get to the point of 5. So this point is 5, 5, which represent the complex number of 5 plus 5i, which is the addition of these two complex number. So a funny thing is that if we add two complex number, we can actually represent them in a diagram, an Argand diagram, as the diagonal of the parallelogram that is made by those two complex number. So similarly, we see this as a vector. So this is 5, 5. Now let's go to subtraction. Let me just delete all the thing I've written. Let's go to subtraction. Let's say we're going to subtraction. So 3 minus 2, that gets us 1, and 4 minus 1, that gets us 3. The complex number is 1 plus 3i. Now I want you to see this line, the line that we connect the 2 points. This line, say from this complex number go to this complex number, we need to move to the right 1 and move up 1, 2, 3 units. So move to the right 1, move up 3 units. So this line is actually equal to 1 plus 3i. And if we see it as a vector, that makes sense, because 3 plus 4, let's say we have this vector 3 plus 4, and 2 plus 1, this vector. So if we want to find what is it going from here to here, we go this way, which is minus this, and go this way, which is plus that, and that gets us 1 plus 3i. So the line that connects the 2 complex numbers is actually the subtraction of this number, subtract this number, and we got this vector. So that is what happened in subtraction. Now let's talk about the modulus of a line. Again, we come back with this complex number 3 plus 4i, and if we represent them in an Argand diagram, 1, 2, 3, 1, 2, 3, 4, this point. Now we want to find the length of this line. The modulus of a complex number is basically the length of this line in an Argand diagram. So this is imaginary and this is real. So this length, so we can find this length is using the Pythagoras theorem, this is 4 unit, this is 3 unit, so this length will be 3 plus 4, 3 square plus 4 square. So we got this line square, we root them, we got the length of this line. In this case, it equals to 5. The modulus of a complex number is basically the length of the line, and that is defined by the roots of x. So this is the real part, x plus y squared, these two squared. So that is modulus of complex number.